here. Okay, so today's discussion is when units matter. And again, we're not going to do calculations for every single one of these. That's a separate video. But really, like I've said before, in a lot of these calculations, the units are super important to avoid mistakes because the IB is intentionally going to change units up to make sure that you're paying attention to the actual numbers and the values that you're given instead of just memorizing a process. And so this is where students miss a lot of points in their calculations, is just because they're not keeping track of their units, and it's easy to not know whether you're done with the calculation or not based on that by not writing your units out. And so the first unit is topic 1, the mole, okay? And one of the things that we do want to emphasize is the idea of Avogadro's number. 1 mole is equal to 6.02 times 10 to the 23. Now, what you need to understand about the word mole is it equals 6.02 times 10 to the 23 of whatever you're describing. So if you're saying 1 mole of ions, then it's 6.02 times 10 to the 23 ions. If you say 1 mole of molecules, then it's 6.02 times 10 to the 23 molecules. The substance does not change when you're converting across there. And so if the substance does change in your question, you have to factor that in as well. Because like if they ask you how many atoms of hydrogen are in 2 moles of molecules, you have to convert to molecules first and then multiply that by the number of atoms within that molecule. So really keep a close eye on these units and make sure that you're converting them correctly. And so when you convert from a mole to molecule to using Avogadro's number or vice versa, the substance you're talking about does not change. And so that's where they'll get you on the first kind of multiple choice question, is they'll kind of ask you like, how many atoms of hydrogen are in 4.0 moles of CH3COOH. And so using Avogadro's number, you can find the number of molecules, but then you have to multiply that by 4 because there's 4 hydrogens for every 1 molecule. And so you have to really be careful because this describes CH3COOH, not hydrogen. So you have to really be careful about that conversion. Secondly, all stoichiometry, okay? All stoichiometry that involves like conversions of one substance to another, okay? All those calculations requires a mole to mole ratio, okay? Anytime you're converting from substance A to substance B, there is a mole to mole ratio required. There is no exceptions to this rule. So if you are converting from a reactant to a product and you have not looked at your balance reaction to get your mole to mole ratio, then you are not done. Now you may stumble across the right answer because it happened to be a 1-to-1 mole to mole ratio, but oftentimes it will not be, just to make sure that you don't accidentally get the right answer. And so you have to have a mole to mole ratio in your calculation somewhere to go from one substance to another way. That's the only way you can convert from one substance to another, is the mole to mole ratio. Now, having said that, for gases, the volume to volume ratio is the same as the mole to mole. Because all gases occupy the same volume with the same amount at certain temperature, at a given temperature and pressure, the volumes can also be the same proportion. So if you have a mole to mole ratio of 1 mole of N2 to 3 moles of H2 gas, that's the same thing as saying 1 decimeter cubed of N2 is equal to 3 decimeters cubed of H2, or even 1 centimeter cubed of N2 to 3 centimeters cubed of H2. These are all the equivalent proportions, and you can use them as conversions in the place of a mole to mole ratio. So that is something that you want to kind of keep in mind, is that to simplify some of these multiple choice questions, they might give you all gases and volumes. You might have to do stoichiometry, but you can use the volume to volume ratio just for gases, not for solutions or anything like that, just for gases, and that is true. Okay. Questions so far? Empirical formula, okay? Essentially, empirical formula is the simplest mole to mole ratio. So your goal, no matter what you start with, is to get an amount of each element so that you can convert to moles. Whether you start with mole atoms, whether you start with grams, whether you start with percent composition, there's always a conversion to get to moles. And so once you get to moles, you divide by the smallest moles to get the ratio. And if your numbers aren't round, then you have to multiply them all by a certain number to make sure you get rid of the decimal place. But the only decimal places you'll have are 0.5 or 0.33 or 0.66. If you get a 0.25 after you've divided by the smallest number of moles, then you did something wrong. Okay. And again, the big mistake that students make is sometimes they'll get the grams of all the substances, and then they'll be like, I just need to get the ratio of these substances, and they forget that that only works in moles, not grams, because 1 gram of oxygen atoms is not the same as 1 gram of hydrogen atoms in quantity. Okay. And also you want to make note is that these are individual elements, not diatomics. So when you're doing empirical formula, you're looking for the number of actual atoms that are present, not the number of molecules. So like H is just the mass of H, O is just the mass of O. Okay. Gas laws, okay? Gas laws are the relationships between P, V, and T. And there's 2 different types of relationships that you have to worry about. One is the combined gas law, which is like this. That shows a relationship when pressure and volume or temperature changes. Now, the units are really important here because pressure and volume just need to have the same unit. Sorry, let me clarify this. Same units across the equation. So as long as pressure is the same on both sides and volume is the same unit on both sides, you can do that. It's just fine. Temperature is the one that really is particular, and the IB will take advantage of your misunderstanding of that, because temperature in your calculation has to be in Kelvin, the absolute measurement of temperature. And so what you need to understand is this: just because the IB gives you a value in a unit and then asks for your answer in that same unit does not mean you can carry that unit throughout the whole calculation. So for example, if they're asking like, what's the final temperature of a gas that starts at 25 degrees Celsius when the volume is doubled, you have to do the calculation in Kelvin and then undo that back to Celsius to get the right answer. You cannot just keep it in Celsius throughout, or you'll get the completely wrong answer. And that answer will show up on the multiple choice as well. So I don't think there's ever a time where you're using a temperature that you wouldn't want to do it in Kelvin. The only time that might even become close is calorimetry, when you're taking the difference in temperature, but the difference in temperature doesn't matter whether it's Kelvin or Celsius. So every calculation that you're doing in chemistry is in Kelvin. Now, may you have to convert to Kelvin and then convert back from Kelvin? Yes. But what you need to understand is that 25 degrees Celsius to 50 degrees Celsius is not double. It's actually just 298 Kelvin to 313 Kelvin, which is very much less than double the temperature. And so you have to really be careful about that, because again, that's part of the skill that you're expected to have in IB chemistry, is understanding, okay, just because I'm starting in Celsius and ending in Celsius doesn't mean my calculation has to stay in Celsius. It always has to be in Kelvin, and then I have to convert back to the answer that I want. So really important you're writing your units out here. Now, the ideal gas law, PV equals nRT. This one is particular in its units. And so this is generally decimeters cubed. Oh, sorry, I wrote in the wrong order. Kilopascals and decimeters cubed is equal to moles times 8.31 joules per mole per Kelvin, which is why the temperature is also in Kelvin. Now, some textbooks will choose to do pascals in meters cubed. That's fine. It's actually the same. These are interchangeable because the prefixes are equivalent. Yes, Marina. Yes, they have to go together. Yes. They might, but there is a conversion for that, for at least decimeters cubed to meters cubed in the data booklet. I think they usually do in kilopascals and meters on decimeters cubed now. Yes, but you're right. These have to stay together if you're going to do conversion here, if you're going to do the calculation here. So really pay attention. I don't think the IB would do this, but I mean, if I'm the IB, I could very well give you pascals and decimeters cubed and see if you actually understand which units go together. So you'd have to convert one of them to match. And again, that's part of understanding units. And that's how you take advantage of students that are just memorizing equations and not understanding what's actually involved in them. Okay. Like other questions? Okay. Solutions. Okay. Now, solution chemistry is dealing with molarity and volume and moles. Okay. And we do understand that molarity is equal to any given moles over any given volume. But I do also want you to make sure you understand that if I tell you something like this in the problem, what that means is 0.500 moles of that substance per 1 decimeter cubed. That's what that translates to. And so sometimes it may be better if you write it like this to help you see it more like a conversion than just this. It's hard to see that this is a conversion when the units are all kind of mashed together. And so I generally write my molarity out as conversion like this on the right, so I can see, oh, I'm converting from moles to decimeters cubed or vice versa. So, but if you're trying to solve for molarity, then you need a certain number of moles and a certain number of certain amount of volume in decimeters cubed to get your molarity. Now, I'll say this though, okay? If you're just comparing, if comparing moles, okay, you can keep everything in centimeters cubed for ease. Meaning that if you don't want to convert decimeters cubed because you're not actually calculating how many moles you have present, keeping everything in centimeters cubed still works for that because it's still showing the same ratio. It's like when you're saying, well, 50 centimeters cubed of 1.0 decimeter moles per decimeter cubed versus 25 centimeters cubed of 2.0 moles per decimeter cubed. These are the same because when I multiply the volume by the molarity, I get the same number. Even if it's in centimeters cubed, I get the same number, so they're the same. Now, you wouldn't want to calculate actual moles with it, but if you're just trying to do a multiple choice question, you're comparing two solutions, then you can just multiply them like that and still be able to compare them. But don't use that for calculations. Okay, it just makes it easier. I think it's easier to deal with 50 and 25 than it is to deal with 0.050 and 0.0250. Yes, Marissa. Oh, like for example, like let's say like they ask you which solution has the most moles of ions. Okay, you could keep everything in centimeters cubed and just multiply them and get the answers. And those answers are the equivalent of comparing them in actual moles. So like let's say, for example, let's just say I had 50 centimeters cubed of 1.0 molar NaCl and 25.0 centimeters cubed of 2.0 molar NaCl. And then maybe 25.0 centimeters cubed of 2.0 molar MgCl2. And I asked you, which of the following has the highest moles of Cl minus ions? Okay, well, for this first one, I would just multiply these across and I'd say, okay, my answer here is 50. My answer here is 50 as well. But my answer here is actually 100 because there's two CLs for this. And so even though I'm not actually calculating the moles, I'm still calculating a number that's comparable. Now, if I ask you how many actual moles were there, yes, you need to convert to decimeters cubed. But if you're doing all of them in centimeters cubed, they're still relative to each other equivalent. Does that make sense?
So yeah. So when you multiply them, like what do you get?
You're not really getting a real
So
unit.
yeah, it's like not really
Yes.
real, because that's not, you don't have to
Correct.
decimeters cubed actually.
Yes. If you're really, actually, it is kind of a unit. It's millimoles, but we don't really use that. I know sometimes if you look in the textbook, they'll say millimoles, but that's, yes, that's
So
so that's
just for
same thing.
this, like, that's
Yes.
how you would do it.
Correct.
But if for some reason you actually wanted to get a number of moles into it, that decimeter,
Correct. Yes. Okay. So yeah, if you're actually doing calculations, you need to make sure the units match. But if you're just trying to compare substances to each other, then keeping them all in centimeters cubed is appropriate or allowable. Okay. Topic 2. This is atomic structure. Okay. Now, average atomic mass. Okay. This is not a units thing necessarily, but it's a thing where I think students, for some reason, have issues sometimes making mistakes about moving the decimal places around when converting a percentage to a decimal. And so whenever I do this, I take out that issue by just taking the percentage times the mass of one isotope plus the percentage times the mass of the second isotope, etc. And I just divide it by 100. And that's my average. You don't divide by 3 or the number of isotopes because the percentage already factors in the weighted average of it. So you just divide by 100 because that 100 fixes all the decimals of the percentages. So I just do whatever percentage I'm given, multiply by the mass, plus whatever percentage I'm given times multiply by the mass, and then I divide that answer by 100, and it always works. Because I think sometimes students will see like this, and then they'll plug that number in, even though in reality it's actually 0.0005 for a decimal form. So some students, when they see decimal percentages, they just assume it stays the same, but no, you still need to move it 2 decimal places. And so take the thinking out of it and just do it this way. Okay. Doing work in your head is your own worst enemy on an exam. It's different when you're in a classroom and it's a relaxed atmosphere and someone next to you can correct your mistakes and stuff like that. But in a test, there's so much stuff going on in your mind. It's so easy to mess up a decimal place, so easy to mess up your reasoning and rationale if you're just thinking all in your head instead of writing down on paper. And that's the kind of stuff that I feel like we can control by writing stuff down on paper like units and trying to avoid that stuff. Okay, it's a difficult habit to develop, but it's something you definitely will notice will prevent a lot of mistakes. Okay, and again, your average atomic mass should be between the masses of the isotopes. If it's outside of the range of the isotopes, then you did something wrong as well. So that's another way to kind of check your answer, is that average should be in between this mass and this mass. No, I would say you'd have to at least approximate it, because they would make sure that there were all the answers would be between the two values, but it's just like how close, right? So like they might say, like, let's say your isotopes are 25 and 27 and your answers are 25.5, 26, 26.5, and like, I don't know, 27. So they'd all be in between, but if you look at the percentages, it'd be kind of obvious. Like if your percentages was 25% 25 and 75% 27, then obviously it's gonna be 26.5, because it's only 26 if it's 50-50. So yeah, you can kind of eyeball it for a lot of times. You can probably eliminate a couple choices, but I would still kind of approximate it at least to try to make sure that you're doing it. But yeah, you don't have to like try to solve and multiply all these numbers out usually. Or if they do, they'll give you percentages that are really easy, like 30 and like 70 or something like that. They wouldn't give you like a 25. Okay. For SO, this calculation, where the speed of light is 3.00 times 10 to the 8th meters per second.
Are we getting that in the data?
That is given in the data booklet. Yes, that is in the whole list table of constants that are provided, which means that wavelength is in meters and frequency is in seconds to the -1. Okay, so please make sure that you're plugging in values right for this. Seconds to the -1, I should say, also is hertz. So if you're looking at problems and sometimes they write it in hertz, that's the same thing. Hz. For higher level, you have to do also include E equals h nu, which is energy, which is in joules because Planck's constant is 6.63 times 10 to the -34 joules times seconds. And again, constants oftentimes are the units that you should really pay attention to the most because the constants are designed so that they make all the units match in an equation. So constants are specifically designed for that purpose. And so if you're writing the units out of the constants, you can definitely see, oh, I'm doing joules times seconds here, so therefore my energy must be in joules when I do this. So again, writing this unit out for every constant can kind of prevent a lot of mistakes. Yes. Mhm. Yes. We will go over that later, but volt is equal to joules per coulomb. So that's how the coulombs cancel out. Okay. Okay. Let's see. Actually, you know, also this is not a unit thing, but this is a calculation thing. This kind of shows up every once in a while in multiple choice is number of orbitals in an energy level. Okay. Maximum number of orbitals, not like filled orbitals, but the number of orbitals in energy level is n squared, where n is the energy level. So if you have the fourth energy level, there's 16 possible orbitals in there. And then the number of maximum electrons is 2n squared, because every orbital can hold 2 electrons. So if you have 16 orbitals, then you can have 32 total electrons in the fourth energy level. So that's just something I was just thinking about with atomic structure. Yes, Jack.
So by energy level, you mean like shells?
Yes. Yeah.
And then orbitals are like the two opposite charge.
Two oppositely spinning electrons. Correct. So yeah, like an S sublevel has 1 orbital, a P sublevel has 3 orbitals, a D sublevel has 5 orbitals. So that makes sense because the third energy level has 9 orbitals. Sorry. Orbitals, because there's 1s, there's 3p, and there's 5d. And then you add another sublevel every time you increase energy level, which is why you steadily increase the number of orbitals by a square factor. That's SL, by the way. Okay. Topic 3. No units in topic 3. That's mostly periodic trends and reactivity and stuff like that. Yeah, I think that's okay. Topic 4 is bonding, and there's not really any units in there either. There's calculation, formal charge, etc., and stuff like that, Lewis structures, but not worth discussing when we're talking about just units. Topic 5, okay? Energetics. This is a big one, okay? There are a lot of units that are flying around in these calculations that are really easy to forget if you're not writing your units out, okay? The big one is calorimetry, okay? Calorimetry is using the temperature change to measure the amount of heat a reaction is absorbing or giving, releasing. And usually it's of water. So you're doing calorimetry in an environment of water. Now, Could the IB change it to alcohol or something like that for this test? Yes, but you do it the same way. It's still the environment, it's still the surroundings. You just have different C value for this. But usually it's involved with water. And when you're doing this, it is all of water. So your temperature change is of the water because you always measure the temperature of the water, not the reaction. The mass is of the water. And again, units matter because they're not going to give it to you in grams. They're going to give you a volume of solution because that's how you measure water. You don't measure the mass of water, you measure the volume of water. And so we make the assumption that 1 centimeter cubed of water or a solution that's predominantly water is same as 1 gram. So they won't give you the mass of the water, they'll give you the volume of the water. And it's your responsibility to know that you need to convert that to grams. Yes, the same value, yes. Yeah, but just so you change the unit, that's all. Yes. Yeah, so I guess that's the one thing, like Marina said, is that they could give you as 0.500 decimeters cubed, and then you're like, oh, I need to convert this to 500 centimeters cubed or 500 grams to do this calculation. Because our specific heat is 4.18 joules per gram degrees Celsius or Kelvin, it doesn't matter which unit of temperature because it's still the same. The difference in Kelvin and Celsius is the same. Like 1 degree of Kelvin is the same as 1 degree in Celsius. Okay. And the mistake that a lot of students make is that the problem does give a mass and they just assume that's the mass you're using, but that mass that's given is usually for the reactant, which we'll use later on, not in this part right here. So the mass given is for the reactant, not for the water. And so you have to ignore that. But students that don't know what they're doing, just know that M equals mass and they just try to find the grams of the problem and they don't calculate it correctly. But then you have to know that Q of the water is the opposite of the reaction. Because whatever's happening to the water is the opposite of what's happening to the reaction. So you need to flip the sign of that to make it of the reaction. And then delta H is Q of the reaction divided by the moles of reactant, which is what you were given in the problem in the first place. And it needs to be the limiting reactant. I don't think the IB would make you, well, yeah, so maybe what they do is they do a reaction and have you identify the limiting reactant and then use it later on in delta H going, okay, what's the delta H? You have to divide by that limiting reactant, not the excess reactant. So you have to be careful about that. Yeah, I would assume so, yes. Yes, Marissa. No. Oh, actually, yes. I think they would say like A, calculate the change in temperature of the water, B, calculate the energy change in the solution, and then C, calculate the enthalpy of the reaction. Yes, I think they would specify like what you're talking about here.
So for that, when you said A is Q water and B is
Well, B and C, yes. I said A is change in temperature.
Oh, right.
Yeah, so yes, B and C you'd flip. Correct. Marina.
So Q is not enthalpy.
No, enthalpy is defined as the heat energy change per mole.
Okay.
So Q is just the energy change of that reaction you've done, but when you divide it by the actual number of moles you reacted, you should always get the same answer no matter how much you react.
Okay, so we take Q, make it negative, we divide it by
The moles that reacted.
and then you also have to get it. It's like changing to
Yes, because if the question asks for it, yes, because your Q will be in joules, correct? Okay. Yes. Again, take the guesswork out of it. Write out the unit and go, okay, if you're doing fact label, just write it out. Don't memorize multiply and divide because again, you're flipping a coin and then you're wasting more time thinking about it than just writing 5 joules here. Or if you're doing proportion method, it's this way, but you just need to still convert it the same way. Either way, it works. Evan.
Let's answer that. Delta H is in
Kilojoules per mole, generally speaking. The IB should state what unit they want it for in the problem. But so like Marina said, you will need to convert your answer to kilojoules. And that's, again, the importance of writing your units out, because I think it's very easy for you to write all your numbers down and just get a delta H and go, okay, I'm done. And not realize that you're not done. You've lost a mark because your answer was in joules. Even if it's accurate, because the problem asked for it in kilojoules, you're losing a mark because you're not following instructions. And they don't know whether you did that intentionally or accidentally. And so they're going to dock you for it. Well, no, sorry. Yeah, if they just did it because they thought that was right versus they forgot to convert. You can't tell that. Yeah, that's probably a better way to phrase it. Okay, but yes, delta H is usually in kilojoules per mole, because when you're trying to find the enthalpy of a substance, you multiply by the coefficient in the substance. And so, like, for example, if this delta H is, I don't know, negative 100 kilojoules, that's per mole of N2, because N2 has one coefficient. But per mole of NH3, it'd actually only be 50 kilojoules of energy, because 2 moles are produced, which makes negative 100. So you can actually treat this delta H as a conversion, just like you would mole-to-mole ratio or something like that. So you can use delta H and the coefficients as a mole-to-mole ratio. Oh, so what do you mean? Well, because what I'm trying to make sure you understand is that this delta H that's listed for this reaction represents the reaction that's given. But what that means is that if I was only making 1 mole of NH3, I would only be producing half that amount of energy, right? Because what they might do is they might do this. Here's a reaction delta H. How much heat is released when 5 grams of N2 are combusted? So you'd have to convert how many moles of N2 that is, and then you'd have to convert those moles into heat, which is when you would do a conversion like, oh, 1 mole of N2 is equivalent of negative 100 kilojoules. Yeah. It's just another way to do stoichiometry. Okay. Now, for HL, delta S, which is entropy, okay? Now, if you're solving for entropy, you treat it like delta H of formation, where it's products minus reactants, except S of elements is not 0, okay? But the problem is that delta S is in joules per Kelvin. And they do that intentionally because what they do is the next problem they do is solve for delta G. And you're using this equation here, delta G is equal to delta H minus T delta S. And a student that's not writing the units down just plugs in all their values and then solves for it, and then they forget that delta G is in kilojoules, delta H is in kilojoules, temperature is in Kelvin, and delta S is in joules per Kelvin, usually, okay? This is why I say it's important to write units, because I don't want to tell you always divide delta S by 1,000, because if I do that and then it happens to be given to you in kilojoules for some reason, then you're going to get the wrong answer.
Yeah, I thought usually you solve for it.
It is in joules, yes. So, but sometimes if you're not solving for it, the IB might give you the value. Like to save your step, it just might say the delta S of this reaction is this. So pay attention to what unit they give to you in. Like if I'm the IB, I give it to you in joules per Kelvin because I don't want a student just plugging that number in and accidentally getting the right answer. So I'm probably giving it to you in joules per Kelvin, but just be careful. Just keep an eye on the units. But yes, Marissa is right. The data booklet is your best friend in a lot of these things because every value in the data booklet, if it's a number, has a unit on it, whether it's delta HF, delta GF, S, bond enthalpy, they're all given in kilojoules per mole. So they're all written out here for you what these units are. And so pay attention to the top of these tables because it's super, super important that you follow through with all this to make sure you get the right answer. Because like I said before, everyone makes mistakes on the test. You just don't want to be losing points for mistakes that you shouldn't be making if they're preventable. You know, I can't prevent you maybe forgetting something like memory wise for the test, but I can prevent you from making a calculation error by not writing your units out, or at least I can try to. Yes, Toby. What do you mean? Oh, this is like enthalpy of reaction, delta G, and like delta S. So it's all the enthalpy, entropy, and Gibbs free energy problems. So like they say, it might say, calculate the enthalpy of the reaction using the enthalpy of formation values given in topic 12, in table 12, excuse me. Or calculate the delta S of the reaction using the values in table 12. Yes, Evan. Yes. Yes. Now, well, okay, let me say this. They will tell you if it's required for you to get the answer. They might not tell you if it's not required for you to use. So like I don't know, like if you're trying to explain trends, you don't necessarily have to reference the data booklet to see how the value of ionization energy changes. But if it's a calculation or they're having you explain something, they will say using this table, explain or calculate. And what that means is that when you explain it, you need to cite values from that table. Like if you're doing IR spectra and they're saying state and explain why there's no presence of a carboxylic acid in this problem, you'd say, well, you are missing a C-Dove O peak at 1700 to 1750. That would be a proof that you using the table that provided. So make sure that you're writing in your answer proof that you actually looked at that table by citing values. Okay. Okay. Topic 6, back to SL material rate, rate of reaction, things like that. Just be mindful of the units of reaction rate. Okay. There are a lot of different units of reaction rate depending on what you're measuring. You know, maybe it's centimeters cubed per second, or maybe it's molarity per minute. You know, just really pay attention to what the units of your rate are in your graph. Maybe they have you calculate the reaction rate at a given time on here, and you've got to calculate this, and you've got to pay attention to what your units are here and what your units are here and what your intervals are here as well. Okay. You know, pay attention to what those intervals are so you read the graph correctly. That is a skill that you're required to have in the IB, is how to interpret and read graphs correctly. And so they will combine this with reaction rate if they want to. So make sure you're paying really close to, because maybe the intervals are 10, 20, 30, 40, but maybe they're 15, 30, 45, 60, or maybe they're 0.5, 1.0, and then 1.5. So really pay close attention to the intervals here. Okay. I don't know what that is. No, it's just like it glitches out sometimes, I think. Okay. All right. Let's pause there. The bell's about to ring. We'll take a 5-minute break and then we'll continue on after that. Okay. So things you have to memorize in topic order from topic 1 to topic 9 and 19. Okay. First, I know it sounds very kind of simple, but knowing all the phase change names is something you're expected to know. And so melting, freezing, vaporization, condensation, sublimation, and deposition, and also know that whether they're endothermic or exothermic, okay, right? So melting and vaporization and sublimation are all endothermic, whereas freezing, condensation, deposition, as you lower energy states, you have to release heat so the molecules can slow down. And don't forget, vaporization is not the same as evaporation. They're not the same. Evaporation happens at all temperatures. Vaporization only happens at the boiling point and above. So be careful about the distinction here. And so here we had this kind of heating curve where you saw how temperature changes. And so what you need to understand here is this. If the temperature stays flat, constant, all the heat that you're putting into the system is going into breaking IMFs, separating the particles apart so the phase can change. But when temperature goes up, now you're within a state of matter and you're just speeding up the molecules. So when temperature goes up, the molecules are speeding up. If temperature is constant, you're adding heat, then you're actually breaking the IMFs and the phase changes actually happen. So phase changes happen at a constant temperature. They don't increase in temperature as you go along. We talked about average atomic mass earlier, but we didn't say that it's relative to 1/12 of a carbon-12 atom, okay? So each proton and each neutron is relative to 1/12 of carbon-12 atom, which is 6 protons and 6 neutrons. So essentially 1 nucleon, I believe is the term that they use, okay? So we talked about these values and then talking about Avogadro's unit as well. Percent composition, okay? Percent composition is the percent by mass of an element in a compound. So it's the total mass of one element in the compound divided by the total mass of the compound, the molar mass, times 100, okay? So if you have two H's, like H2O, you have to multiply the molar mass of H by 2 to get the mass on top, okay? And that's used in combustion and empirical formula problems, okay? Definition of empirical formula versus molecular formula, right? Empirical formula is the simplest ratio of atoms in a molecule, whereas molecular formula is the actual ratio of atoms in a molecule. And they might be the same, they might not be the same, okay? Molar volume, this is given in your data booklet, but it is 22.7 decimeters cubed at STP for the IB. Not 22.4, but 22.7, because standard temperature and pressure is 100 kilopascals and 273 Kelvin, not 101.3. Okay. Other terms, standard solution. A standard solution is one of known concentration. Okay. An electrolyte is any solution that conducts electricity due to the presence of free moving ions. So a strong acid or strong base, a weak acid or weak base, those are electrolytes. There's strong electrolytes and weak electrolytes. Okay, but covalent things that are dissolved, like sugar in water, are not electrolytes. They don't conduct electricity at all. Okay, we talked about our gas laws and the graphs of the relationships between the gas laws, right? An inverse relationship versus a direct or linear relationship. Units of concentration, molarity per decimeters cubed, or even grams per decimeter cubed, or even parts per million in the Winkler method. Okay. Please stop me if you have any question on this. Topic 2, orbitals, sublevels, energy levels. Knowing how many orbitals are in each sublevel and how many sublevels are in each energy level, and then knowing the shapes of the s orbital and the p orbitals. You don't need to know d and f, you just need to know s and p orbitals, because those are the ones that are usually involved in bonding, especially in hybridization when we talk about HL material. A line spectrum versus a continuous spectrum, okay? A line spectrum has specific frequencies of light displayed, whereas continuous all frequencies of light, okay? And a line spectrum relates to the hydrogen emission spectrum, okay? And knowing that when you jump down to n equals 1, it's UV light emitted. When you jump down to n equals 2, it's visible light, and jump down to 3, it's IR, infrared light, okay? You do need to know what type of radiation or light is emitted depending on the energy jump. Okay, you don't have to know the name of the series. I know some of the reviews books will say like Balmer, Lyman, and Pascan, but you don't need to know that. Okay, you just need to know what light is being given off. Okay. Electron. Oh yes, Daphne. Oh, so it's not the electrons, but it's the protons of the Goldfoil experiment. You're thinking of like the Goldfoil experiment is Rutherford's experiment that proved that atoms are mostly empty space, that they were dense nuclei that are very small, surrounded by a lot of empty space, because when he bombarded it with alpha particles, most of the alpha particles went straight through, which means it didn't actually collide with anything significant in the gold foil that was an atom thick, which meant most of it was empty space. But I don't think you need to necessarily know that specific sciences. But yeah. Yes,
Are there any other like experiments?
No, I don't believe so. Yeah, because you don't really need to know the history of the atom and stuff like that. Okay, electron configuration exceptions. Remember, copper and chromium are your big exceptions where you move one electron from the s into the d so that you get a full or half filled. It's only for these elements. And the reason why the IB likes to test you on this is because they like to ask about copper plus 1. Because copper plus 1, you have to know the exception, and you also have to know electrons get lost from the outermost shell to get AR3D10. If you don't know one of those facts, then you'll get the wrong electron configuration for copper plus. So really important you know that exception and that know that you lose electrons from the outermost shell. Okay. You do need to know the Aufbau principle, Hund's rule, and Pauli exclusion principle. Okay. Aufbau's principle is in the ground state of an atom, electrons fill the lowest energy sublevel possible. Okay. And Hund's rule says that if you have multiple orbitals in a sublevel, each orbital gets 1 electron before any of them get 2 to minimize repulsion. Okay. And then Pauli exclusion principle states that every orbital can only hold 2 electrons of opposite spin. Okay. So each, yeah.
The reason for the Aufbau is specifically that, but specifically, I just know how to draw the little.
I feel like I'm almost positive that the syllabus tracker does state that you need to know. Let me double check though, because if it's saying this, okay, let me double check here because now you're saying that. Okay, I'm going to say this. The IB statement does say application of the Aufbau principle, Hund's rule, and the Pauli exclusion principle to write electron configurations. The fact that they stated all 3 of those independently, that's the assumption that you know what each of them does. So they might ask you which rule is being violated in this orbital diagram. Yes, Connor.
But like, since it's just saying like application, like it would just say the past 2 definitions, like it wouldn't just say give us alpha.
No, correct. But they could conceivably ask you, here's an incorrect orbital diagram, state which principle is being, so you still kind of need to know the definition, right? Okay, so Aufbau is excited electrons. So when electrons are too high of an energy state, Hund's rule is when you have like 2 in one orbital before you have 1 in each. And then Pauli is opposite spin usually is the case, or there's 3 electrons in one orbital. Okay. Now, topic 3. Okay. Yes.
So like I listen how you can say how together and not
Well, in Aufbau, what they would do is they'd move 1 electron from the lowest sublevel, like lowest energy state. Yeah, like it might be instead of like 1s2, 2s2, it might be 1s2, 2s1, 3s1. So it'd be at a higher, yeah. Yes, Evan.
How do you work that with like the wouldn't it be 4s1 to be 10? So we would only have 1 in 1.
Yeah, that's an exception there. So they probably won't talk about that. They'll talk about simpler orbital configurations for that. Yeah. Okay. Break's about to start, but topic 3. Okay, know these names of the sections of the periodic table: alkaline metals, alkaline earth metals, halogens, noble gases, your transition metals, your lanthanides and actinides. Those are your F block. Those are the rows at the very bottom. Okay, those are actually kind of easy to remember because they're based on the element that starts each row. So the lanthanides are lanthanum, and the actinides are actinium. So if you don't remember those names, they just start with the element that's in the first spot in that row. Okay. Okay. Let's pause right there, and we'll take the 15-minute kind of class break, and then we'll come back and kind of finish all this material. Okay. So different trends and reactions you need to understand about the trends. Okay. First, ionization energy, understand the definition of it. The energy required to remove 1 electron from an atom in its gaseous state. I guess 1 mole of electrons, I should say more accurately. And this is the example reaction of that. X gas yields X plus gas plus electron, and it's going to be endothermic. Second ionization energy builds off of that. So second ionization energy would be X plus going to X2 plus. Third ionization energy would be X2 plus going to X3 plus. So it kind of keeps going in that same order. Electron affinity is gaining an electron and then the energy change that happens. Sometimes it's exothermic, sometimes it's endothermic. Most of the time for halogens, it's exothermic because halogens have 7 valence electrons, so they want to gain an electron and they become more stable, so they release energy. Mateo.
The electron affinity of oxygen, the second one, I don't understand.
It is positive.
Why is it positive? Why is it endothermic?
Because when you add the first electron, it becomes slightly more stable, but that adds more repulsion, so it actually takes more energy to force you to gain a second electron there. Yeah, but that's overall. Yes, it does want to gain 2, but the difficulty of gaining that second one once you gain 1 is why, like, so if it gained both at the same time, it would be that. But like if you're gaining 1 at a time, there's an additional repulsion with that first electron that's in there. O minus to O2 minus is very difficult. Okay, electronegativity. Measuring the attraction a positive nucleus has for a shared pair of electrons is a relative scale going from 0.7 to 4.0, which is francium to fluorine. Okay, understanding metallic and non-metallic behavior. We talk about this with reactivity. Metals want to oxidize, and so the better they are at oxidizing, the more reactive they are. Non-metals want to gain electrons or reduce, so therefore, the better they are at gaining electrons, the more reactive they are. Yes?
So just like the verification of activity, like the stuff that we have to know that like relies on that is like the polarity relies on that.
Bonding polarity, yes.
Bonding polarity, and then also like when we were doing organic chemistry and like the not systems advanced, but like.
Oh no. You're talking about E and Z. That's atomic number, not electronegativity.
Oh, okay.
Yeah, that's atomic number.
Is there anything else that relies on electronegativity?
No. Okay. Period 3 oxides. Yes, you do have to memorize this, and yes, you need to know general trends that go across this. So your metal oxides like Na2O and MgO are basic in water. They're ionically bonded. They're conductive as liquid, aqueous, and gas. Non-metal oxides like P4O10, SO2, SO3, ClO2O are all acidic, and you need to know those specific reactions in there, and you need to know the difference between SiO2 versus these other non-metal oxides. SiO2 is a giant network covalent, and all these others are simple covalent. So these have very, very low boiling points and melting points. SiO2 has a very, very high melting point and boiling point. But you do need to memorize those 5 reactions because they might ask, just like you saw in your mock exam, they might just literally ask you, state the reaction between sodium oxide and water, and P4O10 and water. And as a note, and I'll answer your question, Daphne, every time you write a reaction, it's implied it needs to be balanced. You should never leave a reaction unbalanced. Like even if you have the right products and reactants, you'll lose a mark for being unbalanced. So make sure you balance every single reaction. Daphne, come on. Okay, when it's pure alkali metals, yes, because there's excess hydrogen that is produced as gas. But when you have a metal oxide, all that hydrogen goes into hydroxide, so you have no gas. Yes. So metal oxides produce just the hydroxide. Pure metals produce the hydroxide and hydrogen gas as a byproduct. Come on.
I believe that you're about to make the states.
Not unless they ask you for it. And the only time I think they would ask you for it is like for enthalpy of formation, where knowing the standard states of the elements is important for that. But if you don't remember them, there's a data table, the periodic table that tells you when the melting points and boiling points are, so you should be able to deduce it from that, right? And so like if you go to the data booklet here and you scroll up, there's a whole periodic table that tells you melting points and boiling points. So the melting point is on top, the boiling point is on the bottom. And so if you want to know the state of matter, it's in that standard temperature conditions, you just look at where's 25 degrees Celsius relative to this, okay? For nitrogen, 25 degrees Celsius is higher than the boiling point, so that means it's a gas. For zinc, it's below the melting point, so it's a solid. So you can use that information to deduce those standard states as well. Okay. But yeah, I think that's only the major time they would ask you to include states, unless they ask you to write an ionization energy where they expect you to know its gaseous state. But they'll say in the problem, including state symbols, write the reaction. So, yes. Oh, sorry. This is Daphne's question, the next part here. So alkali metals react with water to make metal hydroxide and hydrogen gas. Alkalis and halogens form the salt through synthesis. And halogens can replace other halogens if F is the most reactive and I is the least reactive. So if F is by itself, it will displace Cl in the reaction, and F will displace everything, I will displace nothing. Okay? And you can write it one of two ways. You can write it with the sodium, or you can write it without the sodium and just focus on the species that are changing here, the F2 and the Cl minus. That would be more like oxidation reduction reaction. Okay. Higher level. Okay. Topic 13. Characteristics of transition metals. Variable oxidation states. They form complex ions. They form colored compounds. They display catalytic and magnetic properties as well. So why do they form colored compounds? Well, the split D sublevel is formed when ligands bond with them, and when you have a partially filled D sublevel, there are electrons that can jump up to the other part of the split D sublevel and absorb light. You absorb the light that isn't absorbed, you see as a complementary color of the solution itself. The color is dependent on the identity of the metal ion, the oxidation number, and the identity and quantity of the ligand. What the heck? Okay. Topic 4. Okay. Definitions of bonding: ionic, metallic, and covalent. The electrostatic attraction between a variety of things. Volatility: the rate at which a species evaporates. Conductivity: the ability of electrons to move through a species. And solubility: ability to distribute evenly throughout a solvent. Now, remember, all of these physical properties are dependent on the type of bonding that you have and the type of IMF, I should say the type of IMFs that are present. Okay. So things that are weak IMFs have high volatility because they evaporate very easily, like simple covalent molecules, but ionic and metallic bonds or compounds don't evaporate very quickly. Your polyatomic ions, all 10 of them that you need to memorize, okay? And this is explicitly stated by the IB syllabus that you are held accountable for these. Any other polyatomics you are not necessarily held accountable for, and they will tell you information about it. But so these 10 are the ones you need to know. Dichromate, especially for oxidation of alcohol. Dichromate is your oxidizing agent for that, okay? Resonance structures, common resonance structures that I would be familiar with. Now, you don't necessarily have to memorize these, but ones that show up a lot if they're going to talk about resonance structures. Benzene, ozone, carbonate, and ethanoate. They like asking about carbonate and ethanoate and CO2 because they all have C bonds with O, but they're slightly different bonds based on the resonance structure that's happening. And so carbonate, you distribute a double bond across all 3 regions, so it's like effectively a 1.33 bond. Ethanoate, you're distributing the double bond between 2 areas, so it's like a 1.5 bond. So ethanoate's bond is stronger than carbonate's, so it have a longer bond length, a shorter bond length, excuse me, and a higher bond enthalpy. No, there's no carbon at the end after that. So this is ethanoate is a carboxylic acid that's lost to H. So imagine H here, once H is lost, now these oxygens are identical. Now the double bond can fluctuate between these 2 locations.
Isn't that what they mean?
Yes, it is. Yes, yeah. It just happens that the name of the ions of carboxylic acids are exactly the names of the esters. Correct. Okay, Maddie.
I don't understand.
Oh, whenever you change a carboxylic acid into its ion, the ending becomes anoate. OAte, I should say. So like ethanoic acid becomes ethanoate. Propanoic acid becomes propanoate. Methanoic acid becomes methanoate when you lose the H. And that's why in esters, when they lose the H and they form the ester, that's why we call it ethanoate, because it's this part of the ethanoic acid. allotropes of carbon and SiO2. Know the general idea of one, how many carbons they're each bonded to. So like graphite is three carbons each. Olivines are 3 carbons each. Diamond is 4 carbons each. Graphene is 1 sheet of graphite, and these are trigonal planar shapes versus this, which is 12 pentagons and 20 hexagons in a spherical-like shape. Okay. If you want to memorize the term truncated icosahedron, that's also acceptable, but I don't blame you for not wanting to remember that term. Okay. SiO2. So they'll like asking about this because, again, if people don't know what SiO2 looks like, they'll assume it looks like CO2, but it's very different. Each Si is bonded to 4 oxygens singly in a tetrahedral shape, but each oxygen is bonded to 2 Si's. That's why it's SiO2 and not SiO4. Okay? Really kind of tricky thing. Maybe it's me like being guilty of looking at the like Reddit, the RIBO and stuff like that, but everyone seems to be under the impression that this year's test is going to be tricky for some reason, or it's going to be like obscure. Yeah. And so I'm not sure what that means. I just think they're panicking based on what the other stuff they have. I don't know how much obscure stuff you can really get into with chemistry. No, it was really easy. Okay. So, but I will say this. I think it was easy, and I think this one will be probably slightly easier because when you only have 2 papers instead of 3, you have a lot less material you need to study. And when you have a lot less material to study, you can study it more, and so it feels like the test is going to be easier. So like, I don't think it was necessarily an easier test. I just think because they had so much time, because they didn't have to study for an option and stuff like that, they had more time to study, so therefore it felt easier because there was less going on in their brain that they had to kind of recall. Yeah.
Do you think it would ever, like, when the people on Reddit are saying that it's super hard, do you think, like, relative to our mock, that was like, they said?
I think the mock is the hardest that it's ever been. So I don't think it'll be that bad. No. Okay. No, they're just guessing. And the problem is like some of the stuff, like some of those kids don't know what they're talking about. Like honestly, like I've gone in there and answered some questions because like kids will say like incorrect things in the comments, you know? Yeah. Like there was a question like earlier this morning that had like, which of these following can have a cis-trans isomerism? And then some kid out there goes, well, it has to have a double bond to have cis-trans. Like, no, actually it doesn't. Like, and he was laughing, thinking that like it was an obvious answer that everyone should know. I'm like, no, you're actually wrong. It doesn't have to have a double bond. It can have a ring as well. It just has to have restricted rotation. This is HL, don't worry. But it just has to have restricted rotation. It doesn't have to have a double bond. You have to have 4 groups on it, so you have 2 on each side. And so like I had to explain that through there. So hopefully that kid got it, isn't laughing as much now. Okay. So, but that's also the, like, it's funny though, because like, it's one of those cases where sometimes when kids walk out of tests and they say, oh, that was so easy, it's probably because they didn't know as much as they thought they actually, like, it wasn't hard because they weren't actually thinking enough for some of the questions, they were just answering it, and so, like, sometimes it's ignorance when kids, like, sometimes when kids walk out, like, it depends on which kid walks out and says it was easy. Like, there are certain kids in this class, they go out and they said it was easy, I'm like, you just didn't know enough, so you thought it was easy. And then the other kids that said, oh, it's easy. I'm like, okay, you're prepared. I'm not looking at you specifically, Maddie.
Oh. Just me, I walked out knowing very well that I did that.
But so it really does depend on what student kind of comes out. Like if you've been preparing and stuff like that, and you thought it was easy, then it's probably easy. But if some kids go out like, oh, I thought it was easy, sometimes like that it could very well be the case. But if you prepared and you thought it was hard, that means it was hard worldwide. So maybe the boundaries are a little bit lower this year than it was last year. You know, so like boundaries change based on difficulty of test. So it's not always 78 out of 100. Sometimes it's 74 out of 100. Sometimes it's 68 out of 100, right? And so there's leeway for that. So like I said, you kind of want to walk out of there thinking, okay, I did fine. And if you did fine, that means it was challenging enough that you were prepared and you answered most of it or all of it to your best of your abilities. But it's not so easy that some kid that didn't study really hard could somehow stumble into a 7. You want that separation. You want a test that's fair, not necessarily super easy, because an easy test means some kid that didn't study that much could kind of stumble into a 6 or a 7. And that means that every mistake you make is more and more costly. So you kind of want a hard test. I know you don't want to hear that, but you kind of want a challenging test. Okay. Shapes. You have to know your shapes. Now remember, there's only 5 electronic geometries and only 3 for SL, 5 for HL. No matter how many lone pairs and bonding regions you have, they're all the same. So you just add them all together. So if you have 2 lone pairs and 2 bonding regions, that's 4 domains, so it's tetrahedral. If you have 3 bonds and 1 lone pair, it's still 4, it's still tetrahedral. But when you get into molecular geometry, then lone pairs affect your shapes, and that's what's down below this gray line of the shapes you need to know. SL needs to know 6, HL just needs to know 15. Yes, Evan? Yeah.
You don't need to know bonding.
For the most part, no, correct. But you do want to understand that the lone pairs do cause repulsion, which makes the bonding look smaller. So I've seen multiple choice questions where they'll say like less than 120 or like less than 90 and stuff like that. So you do want to keep that in mind. Yes, Estella.
I read that like T-shapes in linear for oxygen don't really exist, like in.
Yes, in reality they do not. But have I seen them go to linear before? Yes. So like that's what, like you're right. Like realistically, it usually doesn't happen. But I feel like there was a time on, maybe it was an old test from before 2016, but I swear there was a time where there was one that ended up being T-shaped for like 6 charge centers, and I was like, because I didn't usually teach T-shaped and linear, but then I remember a test having a T-shaped or linear on there. I'm like, well, we're not supposed to know the shapes, but somehow they still got to that shape. So I teach it just in case. Yeah, you'd have 2 bonds and then 3 pairs of lone pairs, or 4 lone pairs. So you need more. It'd have to be expanded on test. So yes, the likelihood of linear is super like rare, but if you draw the structure and that's what it is, then that's what it is, right? So fall.
Mr. Trong.
With covalent bonding, like coordinate covalent bonding. Lily and then Clement.
Do we have to know the bond angles as well?
For SL, you need to know all the bond angles, yes.
Okay.
But the thing is, if you know the bond angles for the electronic geometry, just subtract 3 degrees for every lone pair you get, and that's your new angle.
Okay.
Yeah, come on.
Oh, good. And I was gonna ask, so the expanded oxide doesn't need to.
Yes, correct. Yeah, this document, if it's red or orange or pink, it's SL. If it's blue, violet, it's HL. So that's throughout this whole document. Yes.
Can you show an example of the
Sure. So data of coordinate covalent bonding happens when an atom has kind of a strange number of bonds that it normally doesn't want. For example, like CO. Okay, carbon monoxide is a good example because when you look at carbon monoxide, oxygen generally only wants to have how many bonds? 2. The fact that oxygen is bonding a 3rd time means that it used one of its lone pairs to bond. So that means that one of these bonds is dative covalent. Okay, so because carbon only has 4 valence electrons, 1, 2, 3, 4. So the only way it can have a 3rd bond is if oxygen donated both of its electrons in a lone pair to form that bond. So anytime you have a molecule that you draw out and an atom has a, lack of a better word, odd number of bonds, like oxygen having 3 bonds or nitrogen having 4 bonds, when it's more bonds than it normally wants to have, that's dative covalent bonding. And also all complex ion, let me do this in blue so it's not confusing, but so all complex ions are dative. So all bonds that happen in complex ions for like transition metal complexes are all dative because the metals have no electrons. So the ligands are always donating its pair of electrons to bond. HL. Oh, the dative covalent part is SL. Complex ion is HL. Yeah.
Complex ions, so that's the one that was like cobalt and H2O.
Yeah.
That like entire chunk of stuff has.
Yes. So the cobalt with the 4 NH3s. Each NH3 is bonded to the cobalt using the lone pair from the nitrogen to form a dative covalent bond.
Oh, okay. Oh, is that not just a single bond?
Yeah, but a normal single bond has each atom donating 1 electron. A dative covalent bond is 1 atom or 1 species donating both electrons. So it's not an equal sharing because both of these electrons are actually owned by 1 species.
Oh,
It's not like, so like here, like these two bonds up here are normal covalent bonds. The bottom one is a different one. That's called dative covalent bonding. It's still sharing electrons. It's just that now you're sharing two of one species electrons, not one of each.
But doesn't nitrogen have it wants to be?
Yes.
So then with cobalt,
No, you're not talking about nitrogen's bonds. Well, you kind of are, but so NH3 has a lone pair on it. And so nitrogen bonding to cobalt is the fourth bond for that nitrogen. So that would be a dative covalent bond.
oh,
Yeah, Isabella. I thought I saw your hand up. Okay. So IMFs, okay? Knowing your IMFs of simple covalent molecules, LDF, dipole, and hydrogen bonding, those are the ones that affect physical properties. So if you're ever talking about a physical property like boiling point or volatility or things like that, you need to address the IMFs in a simple covalent molecule. For HL, topic 14, knowing what a sigma bond is and what a pi bond is, the definition, and being able to identify what they look like in the structure. That sigma bond is that overlap of hybrid orbitals between two nuclei, whereas pi bonding is the parallel overlap of unhybridized p orbitals that are parallel to each other. Okay. Also, your CFCs and NOxes for your ozone. So you need to know those reactions. I don't know if I don't remember seeing these in the last couple of exams, so it may be time for ozone to make a reappearance for the higher level test. So you may want to kind of look at that.
the CFCs, is that salts?
No, CFCs is chlorofluorocarbons. Okay, so when the Cl breaks off in a free radical, it creates this catalyzed decomposition of ozone. Topic 5. This is S element. Enthalpy of formation. Knowing that the energy change when 1 mole of substance is formed from elements in their standard state at standard conditions. I'm recording right now, right? Okay, okay. So if you're going to write an enthalpy of formation equation, you should make 1 mole of compound product made from elements in their standard state, and it's okay to have fractional coefficients because you have to have only 1 mole of product. So it has to be a 1 mole of product. Enthalpy of combustion is when 1 mole of substance combusts with oxygen. For example, like a hydrocarbon combusts, but again, you have to have 1 mole of that hydrocarbon, so everything else has to be balanced in terms of that. So you might have fractional coefficients as well. Yes? No. Why? You have no idea, do you? This is what I'm saying, okay? This is what I'm saying, okay? Know why things are happening, because if you doubt yourself on a test, you're going to be waffling back and forth. What you need to ask yourself is this, okay? An enthalpy combustion reaction has everything you want on the reactant side. So whenever you're given enthalpy of combustion of a substance, that's if it's the reactant, okay? And since everything you want is on the reactant side, then it's reactants minus products, because the products need to be flipped around. In enthalpy of formation, everything you want is on the product side. So that's why enthalpy of formation is products minus reactants. So if I'm to a problem on a test and I don't know which one is which, I'm going to pick any of the substances in the reaction and write out one equation for it. That's it. So like any reaction, I just pick, okay, I'm going to pick this species, I'm going to write an enthalpy of formation or write an enthalpy of combustion for it. And I go, okay, where is it on this in this reaction? Is it on the right or is it on the left? And where is it in the overall reaction? Do I need to flip it or do I need to leave it the same? And whichever one it is tells you which way it is, products minus reactants or reactants minus products. So know that. So formation, everything you form stays the same in the overall reaction, but everything that you react flips around. But in enthalpy of combustion, everything you combust is on the left. So if it's a product of the overall reaction, you have to flip it so it's reactants minus products. Okay? So really be careful with understanding which one's which, because it is very easy to get them backwards, and you need to have that mental check to prevent yourself from doing that, because that's a mark here, a mark there, for getting the wrong sign on delta H. It is 1 whole mark if you have the wrong sign on delta H. Yes?
So basically, it's like the thing that you want, the reaction, that's like.
That's the side, yes.
Okay, so like if you want the reaction.
Yes. Correct. And if you want the products, then it's products minus reactants. Correct. So just write out, pick any substance and write it out as one definition of reaction, and then that'll answer your question without any doubt. Yeah, so bond breaking and bond making is bond enthalpy. So what you have to think there is that on the reactant side, all you do is break bonds. And on the product side, all you do is make bonds. So that means when you break bonds, it's endothermic. So the sign of that side will be positive. But when you make bonds, you release energy. So that means the right side will be negative. Reactants minus products. Mateo.
Oh yeah, if you wanted to just practice, a question from enthalpy, like, where would we go, what should we do?
I would look at old exams. They have a lot of, and also the study guide has, in topic 5 and 15, they have like practice questions at the back of the study guide as well from older exams that you can use as a guide as well. I don't know if I have a bunch of these because you have to be careful because the IB tries to keep it in terms of what's in the data booklet for this. And so you kind of have to look at what's available in the data booklet and make equations from that. But if you do that, you should be able to calculate the enthalpy of the reaction based on any values, combustion or formation or bond enthalpy.
We haven't got a worksheet.
Well, that's what I'm saying though. The problem is like those worksheets usually have enthalpy formations that are not in the data booklet. And so then you're going to have to be looking up those things because I don't give those values in there in those worksheets. But I would definitely look at the study guide, and I can look to see if I have one that's related to the IB practice. But the study guide at the back of the study guide or the textbook itself in topic 5 and 15, and the end of the unit, there are questions about calculating enthalpy formation using enthalpy formation, enthalpy combustion. Okay. Lattice enthalpy, higher level, knowing the reaction between magnesium oxide, like the solid ionic lattice, into a gaseous ions. Okay. So that definition is given in your data booklet, but also know that it's going to be endothermic in that direction. Enthalpy of hydration, going from gas to aqueous ion, and enthalpy of solution is going from solid to the aqueous ion. So it goes through the lattice enthalpy, through hydration to get to that overall product. So this energy diagram, you can go in any direction you want to solve for any of the values you want. And this is what I was talking to one of the students, I was asking about this earlier, is that when you have an energy cycle like this, you can go any direction you want. Like, for example, why does this keep disconnecting? Oh, yeah, it's at 0. So I guess I've been letting it sit for too long. Okay. So the idea is that if you draw the arrow in whichever direction you want, you just need to make the arrows match that direction. And so let me just do this really quickly. So if you want to solve for this arrow here, you just need to go this way. And if you go that way, what that tells you is you need to add the enthalpy of solution because that's pointing in the correct direction. You need to flip all the hydrations to get this arrow. So all these arrows add up in whichever way direction that you draw what you're trying to solve for. So if I was trying to solve for lattice enthalpy here, I would go, I'm starting with solids, I'm going to gas. Okay, do my arrows match in the correct direction which I'm drawing? These don't match, I need to flip them. And then if I add all these up, I should get this value of lattice enthalpy right here. Okay. Now, delta G is equal to delta H minus T delta S. Qualitative application, like the signs of delta S and delta H and knowing when it's spontaneous and when it's not. And again, understanding that you want delta G to be negative. And so depending on what your sign of delta H is and delta S is, you can say, oh, it's always spontaneous, or it's never spontaneous, or it's spontaneous at high temperatures or low temperatures. So don't memorize that whole table of 8 to 12 items. Just be able to apply signs in there and figure out whichever set of conditions that you need to figure out. Yeah, technically 0 is the first point at which it's spontaneous. Ethanol. Well, no, because if it's always spontaneous, that means delta H and delta S are in a manner that no matter what you do, you'll get a negative value. So when it's always spontaneous is
Yeah, but
when,
that's leads to, the only way it would change is to,
Like a sign,
it's higher
like
or
a sign.
Like you asked, like, they asked, in what conditions it was not spontaneous? Like,
oh, okay, because he asked, if it's always spontaneous, temperature doesn't matter.
yeah, okay, yeah, I mean.
But if the signs make it so that temperature is the only thing you can change, yes. Temperature is the only factor that you can affect. Okay.
Now, like, if you're saying that always be
Yes. That's good. Positive, exactly, because you're subtracting it, right?
Yeah.
Exactly. And so then you have to think, you have to ask yourself, okay, if it's not that, then you have to ask yourself, okay, which sign is helping and which sign is hurting? Like if I have a positive delta H and a positive delta S, well, positive delta S is good for me. A positive delta H is bad for me because I want to be a negative value, right? So I don't want my temperature to be very, very high because I want that second term to be so negative that it outweighs the first term. Okay. All right, back to SL, kinetics, okay? Understanding collision theory requires two things, correct orientation and correct energy, okay? What does a catalyst do? It lowers the activation energy of the reaction by providing alternative pathway, okay? And speeding up the reaction rate equal in both directions, lowering the activation energy in both directions, okay? Topic 16, you do need to kind of know your rank order graphs in here as well. So these graphs down here, I think are fairly intuitive because they're just directly related to the rate law. So if you know the rate order, you can just graph these even using a calculator where you say rate is equal to x, or rate equals x squared, rate equals 5. You can graph those. It's these up here where you're doing concentration versus time, where they're slightly a little bit different. And remember, if it's first or second order, the half-life is what differentiates them. If the half-life is the same, then it's a first order. Okay. Also this, Arrhenius equation, we talked about that, and knowing what A is the frequency factor. Factors in the frequency of collisions with the correct orientation. Again, never say more collisions in the IB explanation. Never say more collisions. You always say frequent collisions or more collisions per unit time. One of those two things. More collisions is not an appropriate definition. More frequent collisions is more important. Okay. Topic 7, equilibrium. Okay. When the rate of the forward and reverse reactions are equal, knowing that it's products over reactants where y and x are the coefficients as exponents. And then knowing that reaction quotient is the same calculation, but just not at equilibrium to allow us to know which way the reaction has to go to reach equilibrium. 8 and 18, acids and bases. Okay, know the definitions, amphiprotic for Bronsted-Lowry, conjugate acid-base pairs. Know your variety of acid reactions, acid with a metal, acid with metal oxide, acid with a metal hydroxide, acid with a carbonate, acid with a hydrogen carbonate, and know what the products would be for each of those reactions. Your strong acids, HCl, HNO3, and H2SO4. Your weak base, NH3 ammonia. Your strong bases, group 1 and group 2 hydroxides. Okay. Methods to differentiate between equimolar acids of different strengths, okay? Remember, the concentration has to be the same if you're comparing different acids' strengths. So you can either do conductivity or reaction rate with carbonate or metal, where you can measure how much gas is being produced. Because they'll produce the same amount of gas, it just will be faster or slower. Yes, Mateo?
So I was thinking that strong acids, the base is weak.
Yes.
So does that mean that your NH3 that is a weak base, the conjugate acid is strong?
No, stronger, but not strong.
Oh.
So what that, yeah, so you have to be careful because the conjugate is the inverse, but not so much that it's considered strong. It's just strong, it dissociates more than the conjugate. So yeah, ammonia is a weak base, and the conjugate is still a weak acid, but it's stronger than the weak base it came from. It's inversely related. Yeah.
This is not going with the reaction rate, but like molar mass, is that kind of like the same thing as in concentration?
No.
Like I don't know, like I was going off with this, I was just confusing it as like
Oh, okay, that's Maxwell-Boltzmann, that's not rate of reaction. So Maxwell-Boltzmann curves, what a Maxwell-Boltzmann curve it shows you is the particles in a sample that have a certain amount of speed. Now, that graph is different because unlike having one sample at two different temperatures, this is two different samples at the same temperature. So temperature is based on mass and velocity. So if they're at the same temperature, they have the same total kinetic energy. So if one is slower, that one has to have a higher mass to be the same kinetic energy. So
S is slow.
yes, because if you see its peak, it's at a lower velocity here, average, than this one.
Oh.
Okay, acid deposition. Again, I started the NO2 reaction because that's probably the one that's going to be hardest to memorize. Okay, know your sources and know how to remove sulfur from your sources from pre-combustion and post-combustion. Oh yeah. Oh yeah, that's typo. Yes. Is this charging? Yeah, thank you. Okay, it's charged pretty fast. Okay, higher level. Lewis acid base definition, electron pair acceptor, and electron pair donor, and then buffers. Okay, knowing the kind of idea of a buffer, it's a conjugate weak acid and base pair to resist a pH change in a solution where a small amount of acid base is added. Now, this is something I think I need to correct with Rachel because we were talking about it in individual study, but a buffer's pH is dependent on the weak part of the buffer, not the strong part. So if you have a weak acid mixed with a strong base, it's an acidic buffer. If you have a weak base, I think I told you backwards on the multiple choice question when we talked about tutorials. It was one of the multiple choice questions. Remember I said it was 9.2, it's supposed to be 4.8. You remember which one I'm talking about now? There was a multiple choice that said, wait, what type of buffer, how much NaOH would you need to add to this base, this acid to make a buffer? And what would the pH of that buffer be? And we said it had to be it had to be 10 milliliters, 10 centimeters cubed, but you get a pH of 4.8, not 9.2. I said that wrong. Yeah. So the buffer's pH is based on what part is weak, not the salt or the strong base or the strong acid. It's the weak. So if you have a weak acid and a strong base, it's an acidic buffer. If it's a weak base and a strong acid, it's a basic buffer. Okay. Topic 919, definitions of oxidation reduction. Remember, you either have a loss or gain in electrons, gain or loss of hydrogen or oxygen, increase in oxidation number. And know all three definitions because if the IB states in terms of this definition, you have to be prepared to answer that definition. Even if you use the right explanation, but it's not the right definition, you won't get credit for it. So you're held accountable for all three of these definitions. And so they might ask you, in terms of oxidation number, state why this is reducing. You have to say, well, the oxidation number goes from this to this, so it's decreasing, so it's reduction. But they might also say, in terms of oxygen, why is this reducing? And so you'd be like, well, it loses oxygens, therefore it's reducing. Oxidizing agent and reduction agent. Okay, remember they're the opposite of what the name is. Okay, BOD. Knowing that the molar ratio and that moles per decimeter cubed, you want to convert to milligrams per decimeter cubed. Okay. Voltaic cell, knowing that electrons flow from the anode to cathode in both of them, that both types of cells, electrolytic and voltaic, the anode is oxidation, the cathode is reduction. The only thing that's different is the charge of the electrodes in there. That's the only difference between those two. Yes? No, you do not have to know why. You just have to know that they are. Okay, as well.
So with the sulfurage, like how does it, like with KNO3, for example, is it that like KNO3 is just in the sulfurage?
Yes.
And like there's one end NO3, or is it just that
well,
it happens?
They gravitate toward the side where they're needed.
Oh.
So like whichever side's positive, the NO3 will drift forward, the K plus will drift to the negative side. Yeah. Okay, higher level. Standard hydrogen electrode. Okay, know the characteristics of the SHE. Know that the electrode potentials in your data booklet are relative to the SHE itself. Electrolysis of aqueous solutions. Okay, don't forget, NaCl is tricky because depending on the concentration, you'll have O2 or Cl2 being produced. Now, I do want to add something on here because this shows up in the multiple choice a lot, that group 1 is less reactive than H2O, but Br and I are more reactive than H2O. So if you see, like I've seen that a lot of multiple choice, that if you see a salt that has like KBr or Ki, the I and the Br will react, but the K will not, so the water will react in that case. So keep that in mind. Okay. And then we talk about CuSO4 as another solution where we make different products based on the type of electrodes we have. And last but not least, the three things that affect electroplating for high level are current, duration, and charge of metal ion. Those are the three big things that affect how much you can electroplate. The less you can make, because it requires more electrons per mole. Yes. So the more the current, the more charge you're putting in. The more duration, the more charge you're putting in. The higher the charge of the metal, the more charge it requires for you to make it. So increasing these two increases the amount. Increasing this actually decreases the amount, like you just said. Yes, as well.
So is an electrolytic cell, is it always
Yes, except for the copper sulfate one. Yes. Yeah.
What
Great
is
choice.
the
Oh,
what is that for?
so when you have salts, aqueous salts in water, group 1 metals never reduce in the presence of water. So water will always reduce into H2 gas. But if you have a halogen, if it's Br or I, it will always oxidize instead of water. So you'll get Br2 or I2. Chlorine depends based on the concentration. If it's concentrated, it's Cl2. If it's dilute, then it's O2. Oh, yeah, for electrolytic cells, we usually use inert electrodes so they don't interfere with the reaction. The only time we don't use inert electrodes is when we use copper electrodes in the copper sulfate, where we want the copper to move from one electrode to the other electrode. That's the only time we don't use inert electrodes. Yeah, Mateo.
Okay. And since you still have a cultivation in general for electrolytic cells,
Yeah.
Can you explain how it's so positive? Like how it
No, because what you're doing is you're making it positive to force the elements to give up their electrons. Because in an electrolytic cell, you're doing a non-spontaneous reaction. So your power source is making the anode positive to force the negative ions to go there and give up their electrons. They don't want to willingly give up their electrons. You're making it positive to attract the negative ions to force them to give up.
How does the power source bring
Because we hook it up so that that side gets positive, this side's negative. So we hook up the power source so that the positive, like the electron flow, is going that direction. Yes, Evan.
So is the self-differential of a voltaic cell always positive?
Yes, because it's spontaneous. Right. You'll never have to solve the self-differential of a electrolytic cell. Yes.
For the CO, if it's
Yes. And if it's low, then O2 is produced. If it's dilute, those are the key words: concentrated versus dilute. Okay, yes, Isabel.
So in electroplating, are the electrodes
No. Yeah, I guess not. Because the object you want to electroplate is on the cathode, and the metal you want to electroplate is on the anode. Definitely. Yes. You don't really call it anything. You just call it production of electricity. Like it's producing electricity. It's essentially a battery. You're producing electricity. Yeah, I don't know if there's like. No. Okay.